This program is a presentation of UCTV for educational and non-commercial use only.
Twinkling, twinkling stars of night, how I wonder at the sight. Blue, white, yellow, red, and brown. Stars in billions all around. As we seek, what may we find? Peering into space and time. Looking at numerous stars, can we know of what you are? Common elements are now found, stars in billions all around. Light years distant, oh so far. Can we know of what you are? We are elements of the stars, so familiar, yet so far. There's our own main sequence star. Color spectrum, radiant light. Nuclear fusion in its might.
This is Star Power on Earth, and we're going to be talking about star power at the National Ignition Facility at the lab. I'm Ed Moses. I'm the director of the National Ignition Facility. This is my daughter, Sylvia.
And and I'm a middle school science teacher in San Francisco.
Doing Teach for America. Okay, so let's talk about what we're talking about. We're here in Photon Valley, you know, the place how I think we will be known in the future. This is where the biggest laser in the world is being built, and in fact, it's just being finished right now, right here at the Lawrence Livermore National Laboratory. This is right down the road. It's about a square mile, and you can see in the lower right-hand corner of the screen that big gray building or tan building. That's the NIF. That's what it looks like when you go up to it. This is a beautiful day over the NIF. Our goal is to make a miniature sun on the Earth. That's kind of an amazing thing. If you look up at the sky, the sun is kind of an interesting place. And here it looks through an X-ray telescope, you know, boiling away with its flares coming out. It's about 100 times bigger than the Earth across, which means it has about 1 million times the volume of the Earth. Our goal is to make a very tiny version of it on the Earth and use it for fusion energy. How big? That's how big we're talking about. Something that's smaller than your eye. In fact, the target itself inside that little gold can is about the size of the pupil of your eye on a bright day. What will happen is we'll take lasers and we'll put it onto this target and crush it to the point where it's actually smaller than the diameter of your hair. And when we do, we'll have conditions that exist right in the center of the sun, even hotter, even higher pressures, even larger densities. And when we do that, that's when we'll get fusion to happen, which we'll be learning about today. So one of the questions you might have is, why would you want to build a sun on the Earth? You know, we have one right around the corner in our solar system. Why would we want to have one here? And the answer is kind of clear to all of us. You know, here is a nighttime picture of the Earth. You know, actually it's an assemblage of nighttime pictures that show where all the people live and all the power that is being consumed. And when you think about that today, you think about all the people in China, India, Southeast Asia, Africa, who are living in energy poverty, really, compared to us. They're using about 5 to 10% of the energy we do. And you think about them wanting to have a better lifestyle. Not only that, and the only way they can do it right now is burning carbon, like coal. And when they do, that's going to increase the carbon dioxide in the atmosphere. And we're trying to find a way around that problem for all of humanity.
So, before we begin our journey in learning what fusion energy is, we first need to meet our heroes, Solaris and Photona.
Hi, kids.
Hi, kids.
So Solaris and Photona are our superheroes of the day. They live in the sun, and the sun, as we all know, is one of the biggest sources of energy in our entire solar system. Almost all of our energy comes from the sun. Solaris, the guy, is named after his home, the sun. We say El Sol in Spanish. Sol is the Roman or Latin name for sun. And Photona is named after a photon, and a photon is a tiny particle of light.
In fact, photon is the scientific name that we use for light.
Now, while Photona and Solaris love living on the sun, they go on an annual joy fly through the inner solar system, or the first 4 rocky planets. They stop first at Mercury. Mercury is the closest planet to the sun.
No atmosphere. Very hot during the day. And freezing at night.
They go next to Venus. Venus is almost the exact same size as Earth, but it is really quite different than our nice blue planet.
Look at the big, thick carbon dioxide atmosphere, hotter than a hot oven, and believe it or not, it rains sulfuric acid. No one could live down there.
They skip Earth and head to Mars, our red planet.
No carbon dioxide, no greenhouse gases. It's very cold, and all the water is permanently frozen. It's unlikely that there's any life right now. At least that's what we think.
So finally, after seeing these three pretty extreme planets, they head back to Earth. Earth is the blue planet and Solaris and Photana's favorite planet. It has an incredibly thin atmosphere that we can see in this picture with the light blue ring right around the Earth. And that atmosphere is really important. One of the main reasons why life can exist on Earth is because of the greenhouse gases in this atmosphere. Greenhouse gases include carbon dioxide, and without those greenhouse gases, we would not be warm enough in order for life like us to exist.
This is our favorite place outside of the sun.
But something seems wrong. The Earth seems to be warming. What's going on? Does it have a fever?
Let's go check it out.
So what does Solaris and Photana see when they get to the Earth? Why maybe it getting warmer? Well, the population of our Earth is growing very fast, as all of us know when we look at the crowded living conditions that exist, or when we're traveling on our roads. There's traffic everywhere, and this is a worldwide phenomenon. Or when we look at the smokestacks that are burning coal, oil, natural gas, putting more and more carbon dioxide into our atmosphere. There are other greenhouse gases, but those are very important ones. And this is not the best thing for our planet. There's smoggy conditions in our cities, and this is a picture I took in Beijing about a year ago, where the smog is really pretty intense. In fact, you don't feel too comfortable. And Sylvia was in Nepal, which is a small country in the Himalayas, and in Kathmandu.
Kathmandu is in a valley in between two sections of the Himalayas, and so all of the smog that's going on just gets stuck in the valley. So it is really smoggy. The air almost looks brown.
So what are we going to do about that? Well, it's causing all kinds of other conditions, not just in our cities. You go to the poles or to Greenland or to the South Pole, there are melting glaciers. And this can be demonstrated by something called MOULINS. MOULINS are seasonal rivers that exist on our glaciers. And you can see here water melting, dropping into fissures, and when they do, finally they make the glaciers slide out to the ocean at a faster rate.
I'm so hot, even my ice cap's melting.
So even when we look at this, it has a lot of potential impacts, not just on species here, not on ourselves, but on species all around the world. And in this case, there's some great concern developing for the large Arctic animals besides generally. Also, the tropics are warming up. There seems to be, even though it's not proven, but there seems to be growing damaging hurricanes. And here's the most famous that we've had in our own country. This is Hurricane Katrina winding up in the Gulf of Mexico. And you can see that giant tornado-like spinning going on. And this was tremendously damaging. And this happens because the water in the Gulf is really hot in the summer and early fall.
Holy sunbeam! What's going on down there?
Yeah, that is the question.
Whoa! The Earth is mine!
Here's the carbonator.
What the?
Carbonator. We should have known.
What are you two doing on my planet?
Look at the mess you've made. You should be ashamed.
The humans have chosen me to be their source of energy. These are my oil refineries. This is my coal mine.
And if you look, you see that coal pouring out of that giant shovel. Look at the truck in the middle of the page just to get a scale of how big this is.
Planet Earth is mine. All mine.
Carbonator, you're just acting up again. You used to be a good guy. Snap out of it. Remember, carbon is life.
Yeah, carbon is the food we eat. And it's the beauty of diamonds.
Yeah, but humans are burning carbon so fast that these conditions will only get worse.
Solaris, what do we do? We need to get help.
Kids, we need help from you.
So, the carbonator is a really scary thing. We're burning carbon and releasing it into the atmosphere all the time. We need to think of what we can do to diminish our carbon footprint, to make it much less. So, does anyone have any ideas this morning about what we can do to get rid or stop burning as much carbon? Anyone have any ideas? You can just shout it out.
Solar power.
Solar power, excellent. Anyone else? Wind power, excellent, great job.
Hydrogen power. Wave power.
Ooh, wave power, very good. Good, so I heard recycling, I also heard conservation, solar energy, wind power. You guys are an awesome group. Great job, great thinkers this morning. So let's talk about a few of the ways we already use, or we are already conserving and stopping to burn carbon. So first thing, can you raise your hand if you recycle at school every day? I do, my students do. Great job, way to recycle. We can also use recycled insulation in our houses to keep our houses warm without using as much electricity. We use those crazy looking fluorescent light bulbs, which diminish how much electricity we use. Oh, we also use hybrid cars. Has anyone ever seen a hybrid Prius anywhere? I've been seeing more and more on the road. That's a really great investment. There's also renewable energy. Renewable energy is us taking Mother Nature, energy sources from Mother Nature that are already sustainable and using them. Those include solar energy. This is when we take sunlight that comes directly from our sun and capture and harness it and use it for our energy needs. There's wind energy, which we see on Altamont Pass almost every day. Those are those huge wind turbines where when the wind blows through, it turns the turbine, and we can use that energy for our energy needs. There's hydroelectric energy. That's when we build a dam, and inside that dam, we sort of make a man-made waterfall. And when that water falls down, gravity pulls the water down, it turns turbines, and we can use that energy for our needs. And finally, there's geothermal energy. This is Old Faithful in Yellowstone. It actually takes heat from inside the earth, and we can harness that heat from inside our very own earth to use to warm our houses or to turn into electricity.
These are all fantastic ways to fight the carbonator, but I'm not sure it's going to be enough.
We also can use nuclear power. Right now, about 20% of our energy is from nuclear power plants. Nuclear power plants are actually a totally carbon-free way to make energy. And some countries, like Japan and France, use about 85% of their energy comes from nuclear power plants.
Yes, that is a great idea, but we have another idea that almost everyone overlooks.
What are you guys thinking about?
Well, back on the sun, we use fusion energy. Have you ever heard of that?
Well, I know someone who thought about it a long time ago, actually. One of the most famous scientists, Albert Einstein, when he wrote down his famous equation, E equals mc squared. Has everyone heard of that equation? Right? You know, it wasn't ma squared, it wasn't mb squared, mc squared, where c is the symbol for the speed of light, a really big number. E stands for energy, M stands for mass. Mass is stuff that we're made out of, that everything's made of. And it says that if you can think about energy in terms of mass by just multiplying it by this incredibly big number. So a tiny bit of mass could be turned into a huge amount of energy. Einstein worked this out about 100 years ago.
We learned about this in Solar Garden. This is how you turn matter into energy.
Now, why do you think Solaris and Photona would learn about that when they were just little kids? That's because the sun is a fusion energy plant. That's what drives the sun.
Boy, is that hot.
Yeah, very hot. Near 30 million degrees Fahrenheit.
Right, so what's the temperature in this room in Fahrenheit? 70-ish, right? So this is really hot.
And super high pressures.
Let me show you how this all works, and we'll go over this a couple of times. This is fusion happening right now. We get X-ray energy out and kinetic energy out. And let's just run this back and just keep track of what's happening. So we start with two special types of hydrogen. Hydrogen is the lightest element on the periodic table. Does everyone know where it is on the periodic table? Is it in the upper left corner? Right? And it's not in the lower right, it's the upper left. It's the most abundant one, right? And these are special types of hydrogen, deuterium and nucleus, and tritium. And what you notice about them is they have this positive proton right in the center of their nucleus. It's a really tiny thing, right? And these are the neutrons that are in it. So if we run them together, you know, at very high speeds, but I'm doing it very slowly, at some point, what happens when those protons, those positively charged particles, see each other? Do they like to be together, or do they want to repel each other? Repel. They don't want to go together. And then when they get them real close, they push back harder and harder. So we have to have them moving real fast so they overcome that repulsive force and intersect with each other. And when they do, what is this called? Fusion, right? They're fusing together right here, and what they do is start turning mass into energy, and it happens right here, and you get a big blast of what coming out? X-rays. And then following that, it turns back to helium going off right there. So we make helium, and we get this neutron coming out really fast. So that's kinetic energy. So we get two types of energy out of this reaction: X-ray energy and kinetic energy. That's like a ball moving at very high speeds, and then they go off on their own way. If we can collect those energies, we have now turned mass into energy. So watch the fusion process again. Just let's run it. Here's deuterium and tritium coming together at high speeds, crashing together, putting out a blast of X-rays and a neutron. What is the byproduct of this thing? Is it carbon dioxide? What's that? Does everyone recognize helium? Right? You don't worry about that. That's not a greenhouse gas. That's not a dangerous gas. That's what you would get out of this. So here's the problem of this. I mean, it's not a problem. You turn, you know, hydrogen into helium and energy. That's what fusion is all about. And that's what we're trying to do at the lab.
So we want to make sure, before we go on, we want to make sure you understand that almost all energy in the sun, every star we see in the sky, is powered by fusion energy. Fusion energy is really normal in the universe. We just haven't quite put our minds around it yet. So what we're going to try to do is we're going to try to make a mini, tiny little star inside on the Earth.
We need to bring star power to Earth.
No coal. Sweet.
So how do we make Earth our home away from home?
Meanwhile, back at Lawrence Livermore National Laboratory.
So scientists have been wondering for many years, how can we make this little tiny star on Earth? And it took maybe about 50 years ago, some really smart guys were like, what if we use lasers?
So let's talk about using lasers to make fusion energy. And this is a picture of a laser target chamber at the University of Rochester. It's called the Omega laser, which until recently was the biggest laser on Earth. And there's been experiments going on to do this, getting ready for what's going to happen at the lab. So let's talk about laser light. There's a lot of types of light in this picture. This is a picture taken at the lab. Can anyone guess which is the laser light in this picture? Is it the moon? No. You guys can talk. Is it the moonlight? Is it those red? Is it the red car lights? Is it the fluorescent lights coming out the window? So I guess it's you know, this light going straight up in the air, right? That's a laser light that we shot up in the air to actually help build better telescopes. What am I pointing right here? See this thing? Right? What is this? It's a laser. What isn't this kind of amazing? What's brighter, this laser or that big projector back there? You know, that's putting this thing in. This little laser with a little battery is more bright to your eye because of this very special nature of laser light. We're going to do a demonstration of how cool this is. So the first thing I want to do is try to get an understanding of the difference between laser light and regular light. Let me just show you this picture. Do you think that's laser light, or do you think that's laser light? This is light. Everything is in order. That's laser light. That's regular light. You know, if you think about people, let's build a human laser. Okay, don't you think Sylvia needs a round of applause for the great work she's done? Okay, now we're going to do an experiment. You know, first we're going to give her another round of applause, and then I'm going to say, okay, everyone synchronize. Clap together. I'm not going to give you any clues about how to do that. Just want to see as a group whether we can do it. So ready? Let's give Sylvia another round of applause. Okay, clap together. I want you to know that is the fastest I've ever heard it happen. So what is it? Why were you able to clap together? Right, because you know your ears are listening to sound, and the sound is bouncing off the walls. You're getting feedback around the room. Somewhere in this room, I don't know where, a couple of people started clapping together, and then another few started hearing that, and then we all did it again. Let's do it again. Clap together. Okay. Okay. Now let's see if we can do it if we turn down the gain, so not as much feedback. So let's pretend it's a low power laser. So I just want you to clap with 2 fingers. Shh. Okay, now try to clap together. Okay, let's try it. We've never done it with 1 finger. Let's try that. Try it. Shh. I think we can't tell if we're doing it right. Okay, so at some point there's not enough feedback to make a laser. So that's what's cool about lasers. Okay, let's do one more experiment. There's another thing called amplification, right? That means you take a small amount of sound and make it bigger, or a small amount of light and make it larger. So I'm going to ask one person here, blue shirt, to start clapping with just 2 fingers. How about, 2 fingers. And I want no one else to start until you hear the rest of the room. So when you guys start hearing them, you start going with him, and then it'll spread. Let's see how fast it goes. Pretty fast, huh? So that's the speed of sound in the room. You know, that's the way. Do it again with 1 finger. So we could actually do it just if you listen very carefully. So anyway, you now know everything about the quantum mechanics of lasers. So you're laser experts, right? So now when you look at that picture, what is that? Laser, right? Everything's in order. And that's a piazza in Italy. They're having a better time, but they're like light bulbs, right? Okay, so let's bring up the stage lights and do a laser demo with other things you can do. Okay, so first of all, we're going, this is Chris Ebers. Chris Ebers is a laser physicist at the lab.
Thank you. Grab that little laser pointer.
He's reminding me that I forgot the laser pointer. Okay, so what we're going to do is two kinds of experiments. Chris?
So what we have is a helium neon laser here, and what we're going to show is basically the power of lasers. This laser, although it looks bigger, is actually only about twice as powerful as the little laser pointer that Ed is holding.
Yeah, because that laser technology is from the 1970s, actually, right?
That's correct.
And this technology is from today. And that laser probably cost thousands of dollars when we first bought it, and this one cost
$1.95 in quantities of 10.
That means you make them for free.
Yeah. So that laser puts out 5 milliwatts of power, or 5,000ths of a watt. This laser puts out basically twice that, about 10,000ths of a watt. Now what we've done is we've taken this laser, it starts off small like that laser, we've blown it up so it's a little bit bigger, and then we have a lens. So if you can see here, you can see the beam, and it's going through this lens, and it's focusing to this point right about here. And the point about the laser is that even though it's a very small amount of power, is we can take that and focus it to a very, very tiny spot. And so that the power density, the watts per square centimeter, is actually really high at the point where we can focus it. And then as it goes through the focus, it again starts expanding again.
Okay, so what Chris is saying is that you can, those photons, Photona, remember her, and her cousins, or who are really physical clones of each other, like to act together. And so because of that, we can make a really small spot and do an experiment.
So we have a black balloon, and we're going to put it in the laser beam, and we can hold it here all day long where the laser beam is large. But as we bring it to the point where this very small amount of laser power is being focused very, very tightly, we can pop the balloon, even though we don't have very much power there at all.
And you could not do that with a light bulb. Now sometimes people say, well, is that going on because that balloon is black versus white or something else? And the answer is no. It's really just being absorbed in the plastic. So that it's not the color that matters. If you put a little aluminum on there, it'd be a lot harder to do it because it would reflect the light. But if it were a powerful enough laser, it would just go right through. Do you want to see it again? Do you want to hear it again? Okay, let's do it.
Okay, so again, the balloon is going in. It's where the laser beam is large. Again, we can hold it here all day long. And as we bring it down to that small point where it's focusing,
there you go. So that's how you can use laser light. So we have another laser demonstration that might even be more exciting. Do we have this?
Yep.
Okay, so the question is, could you start a fire with a laser? Well, the answer is we'll find out, but we don't want to burn down the theaters. So we have a piece of paper, right here, and it looks like what to you? We normally just rip up money. This isn't really money. It's just a piece of paper looking like money. We don't want to have a fire, so what we do is we put it in this glass and we put a top on it, so when it catches on fire, everything will be fine. So that's the first safety thing we do. The next thing we're going to do is use an infrared laser to try to set this off, right? Now, would that laser be dangerous to your eyes? Yeah, so we don't want that to happen, so we put it in this glass-like cage. Now, can you see through that cage? So how could that protect your eyes? Well, it only lets visible light out. It doesn't let infrared light out, which is what that laser is made of. So for infrared light, that looks black. So no infrared light is getting out. So, Chris, are we going to turn this thing on?
Great.
So just 1 second. So tell me when.
Yep.
So I want you to count down from 6. Ready? Tell me when to go.
Now.
6, 5, 4, 3, 2, 1. Whoa. You're pretty good. So we can see, we can turn light, we could have a fire from laser light. What is laser light doing? And if you do this, what? We're transmitting energy over a distance using electromagnetic light, beams, right? That's what's so cool about it. And that's why I can put this up here. Can everyone see it? Or up here? you know, and you can still see it. It's a little tiny light. If I turn on the flashlight, see this flashlight? Does everyone see that flashlight? This is safe to do, right? You can see that? Right? So if I fire that at the screen, just barely. If I turn it into a laser, pretty cool, huh? Now you know a lot about lasers. So you know about the physics of lasers, and you know about how they can transmit energy. So the next thing you have to know is, remember in the beginning we showed you how we had to crush a balloon, we had to crush that little target real small? So we're going to bring out a target right now. Can we have the stage lights, please? And we're going to bring out some little laser beams. Come on out, guys and gals.
Uh-oh.
Oh, don't break it.
No, we got a spare.
Okay. So come on up here, and I want to have our safety moment for you. So we're now at the edge of the stage, so we don't want to go close to the stage edge. Okay, you're going to have to call out your names real loud.
Vishant.
Your name?
Brandy.
Brandy?
Nicole.
Nicole?
Morgan.
Morgan?
Rachel.
Rachel?
Vaughn.
Okay, so these are our little laser beams. And so Sylvia and Chris and I and the little laser beams, the clonettes, if we were trying to do fusion, we would want to take this size balloon and make it that big. Do you think they can do it? You think so, huh? Well, we'll see. Okay, so go around the balloon, and I'm going to stand here because I don't want anyone to...
And I want you on the fence.
Okay, so we're not jumping back off the stage here, okay? So can you guys go over to the side a little bit? Okay, so I want you to just not use your nails or anything. Push on the balloon, right? And see if you can crush it. And here's the problem. What happens? Push, just gently. Okay. What's wrong? Is it crushing up nice and smoothly? No? Okay, why don't you use your bodies, put yourself closer to it and try to use your legs. Now push. Whoa! Exactly the problem.
Good job, guys. Okay, take a bow, take a bow.
So they didn't make it that big, did they? Okay, we're going to walk carefully off the stage. Thank you very much. Let's give them a big round of applause. What's the next thing we do? Okay, so that's the problem. How would you find a way to crush up something not that big? Of course, it starts out tiny, but make it equivalently that small. So make it around 1,000,000 times smaller volume without having to squish up and blow apart ineffectively. So let me just show you what we do. This is a laser target. It's in a gold can, and it has that hydrogen that we were talking about right in the middle. And what we're going to do is use laser light to do the experiment we just did, except hopefully a little better than they did it. So the laser light from the big laser comes in. See those billionths of a second going by? It's kind of interesting, not hundredths. And what we're doing is making a super hot oven. And this oven is having X-rays come hit that target, think of that as the balloon, and push on it and push on it and push on it until it becomes a star or a sun on Earth. Does everyone want to see that again? Okay, so let me see what we can do here. I'll do it slower motion, right? So here is the gold can. Now think about that right now. That's the balloon, and this is where the ice is, and here's the laser light, and the laser light is coming in, it's heating up that gold can, right? Now we'll take it further, and this is those kids pushing on the balloon right now, except you see we have lots and lots of them, so it pushes it in very smoothly, and it pushes it and pushes it, and now it's getting smaller and smaller, smaller and smaller and smaller. The temperature is getting hotter and hotter and hotter. So in fact, it's up to 100 million degrees. And when at this point, it's just like the inside of the sun, and we get fusion to happen. This is the real target chamber where the fusion is going to happen at the lab. Do you see that guy down there? See how big this is? This would sort of fit in this room, maybe. right? And those big cans are where the laser light comes in. Let's see how this works in real life. So are you ready to turn this on? So watch here. So we have a camera looking inside, there's smoke, there's the laser beams, or like the laser beams. Can you see it? And then you see that target go off. So that's the idea, right? Is everyone an expert in fusion now? You're an expert in lasers, I know that. Get that whole thing? Okay, why don't we do it one more time? Okay, so we have smoke come in so you can see the laser beams. These are very low power lasers, nothing to worry about. You can see the 192 laser beams coming in, heating up that target, bam. Okay, so when we talk about burn here, it's different than the kind of burn we saw over there. That was chemical burn, right? You know, oxygen was heating up was mixing with the carbon in that paper and burning. This is a very different kind of burn. This is nuclear burn. So this is the National Ignition Facility. Does anyone know how big that is? Anyone have an idea? It's that big. You could have 3 full football fields on that laser. Not like this laser here, right? This is a little tiny one. So what we do here is we take the roof off and just look how it would look inside. And we have laser light that goes back and forth. It gets extremely powerful. The highest energy and highest power laser in the world goes to that target chamber. I'm just going to stop this when we do it again. That target chamber is, you know, the big version of this, the one we saw that blue ball, and this is where it all happens. So there you go. Bam. That's where we do the whole thing. That's where the fusion happens. Some people ask me, how long does it take to get this fusion burn to happen? Well, it takes not 1,000th, not 1,000,000th, not 1,000,000,000th of a second, but a few trillionths of a second for it to all happen. So this is really quick. This is not a blink of an eye. So this is how it really looks in the control room when we're running NIF.
Start the countdown for shot on my mark. 3, 2, 1, mark. Clock is running. 3, 2.
This is a real countdown.
Shot.
Okay, now we're in a cartoon. This is going at about 1/1,000,000th of the speed it goes. And look at this. This chunk of light is around 20 feet long. It's hard to believe. So if you took a movie of NIF, you would see a chunk of light going through it. And it's going through that glass. Most amazing thing about NIF, it actually plays music as it happens. I'm just kidding. Okay. So now we're heading towards the target. And remember, this is going at the speed of light, really. And something amazing is about to happen. This infrared laser, like the one we had over there, is going to turn green right here, and then blue, and then we're focusing it, just like we did over there, onto this target. So this is a huge amount of energy. And you watch the billionths of a second going by, and this gold can is getting really hot, millions of degrees, just like the sun, right? It's putting out these X-rays that are driving this target into be very small, very fast. That target is moving in at 1,000,000 miles an hour. I'll talk about that in a second. And when it gets really small and really hot, it blows, right? Remember that when it happens is smaller than the diameter of your hair. So people often ask, well, you know, are you going to build a sun on the earth? Is it going to blow up the valley or something like that? No, this is really tiny. But if you do it over and over again, you can get electricity out of it.
5.
This is actually how it looks, not a cartoon.
3, 2, 1, shot.
It actually makes noise. And this is in super slow-mo. Sounds like the carbonator's cousin. So that was 3 views of one shot. So our goal is in the next 2 years, we're just finishing the NIF literally in the last few weeks. The facility is built and we're starting experiments to do fusion in Livermore at the National Ignition Facility in Photon Valley, right? And hopefully someday we'll be able to have this in New York,
Cairo,
Sydney,
in Australia,
San Francisco,
right on the hill,
Seattle,
keep Bill Gates warm in the winter,
Paris,
you know, good food cooked by NIF-type electricity.
Shanghai.
Now, I always like this picture of Shanghai. Does this look like a city of the future? It actually is a picture of Shanghai. It's an incredible place. You know, if you ever get to go to China, it's really interesting.
Maybe everywhere.
Yeah, this is our goal. Could we provide clean, limitless, carbon-free energy for the world in the future? That is one of our big challenges as a species. This is all of our challenges.
Well, I'm very excited.
This is the governor at NIF.
This little more laboratory, which is, of course, the most spectacular and innovative place in the world. And I think it is because of all the great work that is being done here. I mean, everything that's being done here for the last 50 years, I mean, it has been extraordinary, and it has had a huge impact on the world. And I think that right now, why I have come here is because of the fusion and of the kind of development that's going on. It goes in the direction of creating new energy, and energy without any greenhouse gas emissions. And this is what I promised the people of California when I became governor, and I'm going to continue on searching for that and build up, you know, the renewable energy here in California. But this fusion power, I mean, when you think about it, the amount of energy this will create, 1,000 times the amount to power the whole United States, that's huge. So I love it. Thank you for the great work you've been doing.
Let's hear it for the governor. I mean, that was great. You know, now the governor was an important visitor, but we had a much more important one right after he came.
Great work, people of Photon Valley, pursuing clean energy. I'll be back.
Looks like people in Photon Valley know what they're doing.
It's a good start. They have a lot to do, but I'm sure they can do it.
I don't know what I was thinking. Thanks for getting me back on track. I needed that.
It is the green carbonator.
No problem. It's good to have you back. Well, see you later.
Okay, see you guys around.
Say goodbye, kids. Back to the sun. So I want to thank you all. We're going to roll the credits here.
Wow, wow, the earth is mine. The earth is mine. The earth is mine. The earth is mine.
What the?
What are you two doing here on my planet?
Carbonator! We should have known.
I am the human's #1 choice for creating energy. These conditions will only get worse.
Should have known.
What?
Planet Earth is mine. All mine.
Solaris, what do we do? We need help.
Back on the sun, we use fusion.
Einstein figured this out years ago.
What we need to do is bring the star power to Earth. It can provide power for your homes.
No coal.
For your home.
Sweet. No coal.
Fusion for your home.
Fusion happens in all the stars. This is where the energy of the cosmos comes from. Fusion powers the universe.
Fusion